Howdy, this video is on periodic trends. The periodic table is one of the most powerful tools for predicting how elements behave. The periodic trends illustrate how characteristics of elements vary as one moves across the periodic table. The periodic trends enable us to predict which elements are larger, more likely to lose an electron, more likely to gain an electron, basically how the different elements react. What I want you to be able to do after watching this video is be able to describe how the electrostatic interaction between the outer electrons and the nucleus varies as moving across the periodic table. Describe how the size of electrostatic interaction between the outermost electron and the nucleus is related to the size of the atom, electron negativity, ionization energy, and electron affinity of the atoms. Put a list of elements in order of increasing size, electron negativity, ionization energy, and electron affinity. Describe how an atom gets smaller when an electron is removed and gets bigger when an electron is added. Put a list of ions in order of increasing size, electron negativity, ionization energy, and electron affinity. So electrostatic interaction is just the interaction between charges. Like charges repel, opposite charges attract. And electrostatic interaction follows Coulomb's law, which says that the force between the particles is equal to K, a constant we don't care about, charge of particle 1 times charge of particle 2, divided by the distance between the charges squared. And so the larger the charges, the stronger the force, the shorter the distance, the stronger the force. And so the stronger electrostatic attraction, the lower the energy, the more stable. The stronger electrostatic repulsion, the higher the energy, the less stable. And so electrostatic interaction is essential for understanding the energy of electron orbitals, but also size of atoms and ions, ionization energy, electron affinity, and electronegativity. And so if we think about the periodic table, as you go down the periodic table, electrons are going into bigger and bigger shells. Remember, as you go down, electrons are going in shells with bigger N. N denotes the shell, but also indicates the size. And so as you go down, atoms get bigger. As you go from left to right, you're increasing the number of protons in the nucleus, and so the atoms actually get smaller. And so if you combine those two concepts, as you go up and to the right, atoms should get smaller. As you go down and to the left, atoms get bigger.
It is possible to estimate the radii of atoms in characteristic bonding situations by observing the distances between atoms in molecules. In any given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
And so as you go from left to right, you increase the effective nuclear charge. You're increasing the nuclear charge because more protons are in the nucleus, but remember there's also going to be some shielding. And so again, combining the two concepts of going down, electrons going in the shells with bigger N, bigger size, and going from left to right, more protons in the nucleus, smaller. And so that means as you go up and to the right, atoms get smaller. As you go upper right to lower left, atoms do get bigger. Kind of cool. It's just from these two basic concepts. Now this periodic table is actually colored based on the covalent radius. And so the basic idea is there's different ways of characterizing the size of an atom. One way is you look at a diatomic molecule built by two atoms, and then you look at the distance between the nuclei, divide by 2, and that gives you the approximate radii. And so for the covalent radii, as you go up to the right, you see a lighter color yellow, means that the covalent radii actually gets smaller. And so fluorine has a covalent radius of 0.57 angstroms. Francium is 2.6. And so francium is about 5 times bigger than fluorine. And so as you go up to the right, the electrostatic interaction between the electron and nucleus increases, and the size of the atoms decrease. Now, if we think about forming cations, which are positive ions, that means you have to remove an electron. Remember that electrons can cause shielding, and so if you remove an electron, you reduce the amount of shielding, and so the positive ions are always going to be smaller than the atom that it came from. Now, if we add an electron, there's going to be more shielding, and so there's going to be a weaker effective nuclear charge, and so negative ions are always larger than the atom that they came from. And so again, please remember, this is all about shielding. If you remove an electron, you reduce the amount of shielding, so stronger effective nuclear charge, so positive ions are always smaller than the atom they came from. If you add an electron, you're increasing the amount of shielding, and so negative ions are always larger than the atom that they came from. Now, you could be asked, put the following in order, increasing size. And so we saw that as you go up and to the right, atoms get smaller. And so you have magnesium, barium, magnesium, fluorine. And so we'd assume that barium's the largest and fluorine's the smallest. And that's exactly what we see. And so in increasing size, we'd say fluorine, magnesium, barium being the largest, fluorine being the smallest. And so if you're given atoms with no charge, then you just use the periodic trends. Now, you could also be asked about ions. Now, this is a little bit different. We cannot use the periodic trends when we have ions. It's still going to be about the electrostatic interaction, right? So for atoms in size, the electrostatic interaction between that electron and the nucleus is mapped onto the periodic table. That's why we can use the periodic table for just atoms without a charge. For ions, we have to look at the electrostatic interaction by looking at the number of protons and the number of electrons. And so the number of protons is just equal to the atomic number. Now, if oxygen has got 8 protons and oxide ion has -2 charge, that means that the oxide ion must have 10 electrons. Fluorine, 9 protons, minus charge means 10 electrons. Magnesium, 12 protons, plus 2 charge, meaning it has 2 less electrons, and so it would be 10 electrons. And so we'd say that this series of 5 is isoelectronic. They have the same number of electrons. And so the stronger the electrostatic attraction, the smaller the size. And so if we look at it, the biggest number of protons should give us the stronger attraction, right? They all have the same number of electrons, so they should have the same amount of shielding, but the more protons in the nucleus, the stronger attraction, the smaller. And so the magnesium +2 should be the smallest, and oxide ion -2 should be the largest. And so if you have ions or atoms, it's still about the electrostatic interaction, but again, for atoms, you can use the periodic table because it maps the electrostatic attraction. For ions, you have to look at the number of protons, number of electrons to determine the relative strength of the electrostatic attraction between the outer electron and the nucleus. And so we saw that the strength of the electrostatic attraction, outer electron, nucleus depends on periodic trends. We saw that as you go up and to the right, the strength of the electrostatic attraction between outer electron and nucleus increases as you go up and to the right. The size of atoms also decreases. And now in terms of ionization energy also depends on the strength of electrostatic interaction between the outermost electron and nucleus. Ionization energy is the energy required to remove an electron from an atom ion in the gas phase. Ionization energies are always positive because it always takes energy to remove an electron. And so here we have potential energy. This is magnesium. And so you can imagine that if you had the electron by itself, it would have a very high energy. And so the first ionization energy, first means the energy to remove that first electron, would be the difference between here and there. And for magnesium, that first ionization energy is 738. Now, once you remove the first one, you're left with magnesium plus ion. Now to remove that second one is going to take up a little bit more energy. And so you've reduced the amount of electrons going from magnesium plus. So you've also reduced the amount of shielding. And so that's why I2 should be greater than I1. And so again, I1 is the first ionization energy required to move that first electron. I2 is the second ionization energy required the second electron. And again, I2 is always going to be greater than I1 for a specific element because it's always going to take more energy because you reduced the amount of shielding when you remove that first electron. Now to remove the second electron, it's going to take even more energy because that's the last electron. So to remove that second one, it's going to take more because again you've reduced the amount of shielding. And that was 1451. To remove the third, you're going to actually have to go to the 2p subshell, right? So the first two were removed from the 3s subshell. Now we're moving from the 2p, and what we see is a dramatic change in how much energy it takes because you went from the third shell to the second shell. Now this just takes too much energy, so typically magnesium forms the +2 ion. But always for element, I1 is less than I2, which is less than I3, etc.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy, I2. As each electron is removed by ionization, the remaining electrons experience less electron-electron repulsion and a greater effective nuclear charge. Thus, each successive ionization requires more energy. This graph shows the way in which the ionization energies of the aluminum atom increase as successive electrons are removed. Notice that the ionization energy increases with each successive removal of an electron. However, there is an especially large jump in the energy required for removal of the fourth electron. From a knowledge of the electron configuration of neutral aluminum, can you account for this dramatic jump?
So looking at the aluminum ionization energies, so after you remove the first one, I2 is greater than I1, and I3 is greater than I2. And so the first three electrons are in the same shell. And so after you remove that first electron, you're going to reduce the amount of shielding, and so there's going to be a stronger electrostatic attraction. Now to remove that fourth electron, you'll have to dip into a lower shell, and so that would take even more energy. And so for aluminum, it typically forms a +3. A +4 would just take too much energy. And so here we have a table of ionization energies. Again, I1 is the first ionization energy, I2 the second, I3 third, etc. And again, this is energy required to move an electron in the gas phase. It's very important that you know it's in the gas phase. Now I2 is always going to be greater than I1. If you look at beryllium, it often forms a beryllium +2 ion. And so you have to remove the first electron and the second electron. And to form the beryllium +2 ion in the gas phase would take 2,657 kilojoules per mole. Now hydrogen only has one ionization energy because it has only one electron. Going from left to right across the periodic table, generally the first ionization energy increases. Nitrogen is an exception because nitrogen has that half-filled subshell of the p orbitals, and so it's a little bit extra stable, and so it takes a little bit more energy. If we look at oxygen, again, I1 is always less than I2, always less than I3, always less than I4 for a specific element. Now it's kind of interesting. So the red ones correspond to removing the electron from the 1s orbital, the blue ones for the 2s, and the green ones would be the 2p. And again, notice that these numbers are all different because you have a different number of protons, and so the energy required to remove an electron is going to be different. The energy required to remove an electron depends on the charge of the nucleus. It also depends on how many electrons you have, because that affects shielding. It takes more energy to remove the second electron from the 1s or 2s orbital than the first because of shielding. And so here we have lithium, beryllium, boron. And again, notice that for lithium, it doesn't take that much energy to remove that first electron. It takes a lot of energy to remove the second one. And so lithium and alkali metals tend to form +1 ions. For beryllium, not too much for the first one or the second one. It takes a lot of energy for a third one. And so often alkaline earth will form +2 ions. Boron, not too bad for the first 3. That fourth one a lot, and so sometimes boron would form +3 ions. And so the energy cost is very high to dip into a shell with lower N. So when you remove that first electron from lithium, you're doing it from the 2s orbital. The second electron, you're actually taking it from the 1s orbital. And we see the same thing with the next row. Sodium typically forms a +1 ion because to lose that second electron just takes too much energy. Magnesium tends to form a +2 ion because, again, to lose that third electron takes way too much energy. And aluminum typically that forms a +3 ion because to go to alumina 4+ would just take too much energy.
The first ionization energy is the energy required to completely remove an electron from a neutral atom. Ionization energy generally decreases as we move down a group because the outermost electrons are increasingly distant from the nucleus. Less energy is required to completely remove the first one. As we move from left to right in a given row, the ionization energy increases dramatically because of increasing effective nuclear charge. Notice the periodic character of the change in ionization energy as we move across each row. As we move across the first transition element series, the ionization energies increase slowly in proceeding toward the right. The same trend of increasing ionization energy across the transition series is observed in the second long row, consistent with the periodic character of this property.
And so as you go up and to the right, typically ionization energies increase. There are some exceptions, and so when we say periodic trends, we do mean trends. There will always be some exceptions. And so this table is colored based on the first ionization energy, the energy required to remove that first electron. And so as you go up into the right, the electrostatic interaction between an electron and nucleus increases, size decreases, ionization energy increases. So we saw for the alkali metals, it doesn't take a lot of energy to remove that first electron, so they tend to form +1 ions. Hydrogen is not an alkali metal, even though it's listed right above them. It's also listed above the halogens. Hydrogen is not a member of any group. The alkaline earth, it doesn't take that much energy to remove the first 2 electrons, so they typically form +2 ions. And we saw that aluminum tends to form a +3 ion. And so some elements gain electrons to form anions, and some elements lose electrons to form positive ions. Now, electron affinity is the energy released, emitted, when an atom or ion gains an electron in the gas phase. So for both ionization energy and electron affinity, it is defined as being in the gas phase. And so if we think about chlorine and the chloride ion is actually a little bit more stable than chlorine atom. And so that's why you'd actually release energy going from the chlorine atom to the chloride ion.
Electron affinity is the energy change that occurs when an electron is added to a gaseous atom or ion. For example, when an electron is added to a neutral gaseous chlorine atom, 349 kilojoules per mole is released. In the case of chlorine and the other halogen elements, addition of an electron to the neutral atom is an exothermic process. Addition of an electron to the neutral oxygen atom is also an exothermic process. However, addition of a second electron to form the oxide ion is an endothermic process. This means that work must be done to force an electron onto the singly charged ion to form the oxide ion, O2-.
So it's kind of interesting. We saw that for ionization energies, those are always positive because it always takes energy to remove an electron. Now what we're seeing here is for electron affinity, energy released, that what means by exothermic. It's positive for, say, chlorine and oxygen. Now once you add one electron to oxygen, then the electron affinity becomes negative, and so you actually have to add energy to add that electron. And so here are tables of electron affinities. And so the ones in red are nonmetals. They tend to have large electron affinities. They really want electrons. Nitrogen is an exception. Remember, it was an exception for the trends in ionization energy. It's an exception for electron affinity. Again, that half-filled subshell of p orbitals is extra stable. Most electron affinities in the gases cannot be determined because they tend not to gain electrons. If alkyl metals gain electrons, their outer s orbitals fill. Nonmetals tend to have larger electron affinity than metals. So the nonmetals are in blue, the metals are in red. And so what this means is that typically nonmetals react by gaining electrons. And metals typically react by losing electrons. And so as you go up and to the right, the electron affinity increases. And so this periodic table is colored based on electron affinities. Again, the darker blue is the more positive ones, and so we see the halogens have very positive electron affinities. The ones in white weren't determined. The lighter the color, the smaller electron affinity. And again, notice that nitrogen has electron affinity of -7. So other than nitrogen, I think all the electron affinities that we saw on the table were positive. And so as you go up and to the right, electrostatic attraction between the outer electron and nucleus increases. The size decreases, ionization energy increases, electron affinity increases. So all these are about the strength of electrostatic attraction between the outer electron and the nucleus. And the last periodic trend that we're going to talk about is electronegativity, which is symbolized by chi. And electronegativity is the ability of an atom in a molecule to attract electrons to itself. The greater electronegativity, the greater atom's ability to attract electrons to itself. It's actually a concept proposed by Linus Pauling. And we'll use it throughout the semester, so please make sure you understand what electronegativity means.
An atom attempts to attract electrons toward itself when bonding with another atom. The level of attraction of each atom is called its electronegativity. When sodium and chlorine react, the chlorine atom removes sodium's valence electron and becomes a chloride ion. The less electronegative sodium atom cannot compete for electrons and becomes a sodium ion. The attraction between the ions is an ionic bond. When bonding atoms have nearly equal electronegativities, neither can attract electrons away from the other. In a carbon-sulfur bond, the electron pair is shared almost equally between the two atoms, resulting in a covalent bond. When hydrogen and oxygen react, the more electronegative oxygen atom cannot completely remove an electron from hydrogen. The shared electrons are attracted more to the oxygen than to the hydrogen atom. This unequal sharing is called a polar covalent bond. Polar bonds have a slightly negative and a slightly positive end.
And so electronegativity is the measurability of an atom in a molecule attracting electrons to itself. And so if the difference in electronegativity is between 2 and 4, then there's actually a transfer of electrons from the metal to the nonmetal. If the difference in electronegativity is really small, say less than 0.5, then the bonding electrons are equally shared. If the difference in electronegativity is between 0.5 and 2, then we consider it unequal sharing or polar covalent. And so the electronegativity is important because we can use it to determine if a bond is ionic, covalent, or polar covalent. And so we can again color the periodic table based on electronegativity. Now notice that all of your periodic tables, the ones on the front page of the worksheet, electronegativity is right below the symbol. And so fluorine is the most electronegative with an electronegativity of around 4. And as you go up and to the right, again, electronegativity increases. So as you go up and to the right, electrostatic attraction between the outer electron and nucleus increases, size decreases, ionization energy increases, electron affinity increases, electronegativity increases. And so all these are related to the strength of electrostatic interaction between the outer electron and the nucleus. Now if we think about it, we saw that on the upper right, the atoms are smaller, they want more electrons, and so these guys are the nonmetals. The nonmetals tend to react by gaining electrons. And we saw down on the lower left, they had smaller ionization energies, and so they're more likely to lose electrons. And so the metal elements are the ones in red, and they tend to react by losing electrons. The ones in yellow are the metalloids, and they tend to have a behavior somewhere between a metal and a nonmetal. And so we saw that the ionization energy for the alkali metals wasn't that high, so they tend to form +1. The alkaline earths tend to form +2. Fluorine and the halogens tend to release energy when they get electrons, so having a fluoride minus ion is more stable than a fluoride atom. And so the halogens tend to form -1 ions, and the chalcogens tend to form -2 ions. So here's a type of question that you can be expected to be asked. So what group does fluorine belong to? And so to answer this type of question, you have to remember the names and symbols for the first 4 rows of the periodic table. Remember, you're always given a periodic table, but it's not helpful unless you know, say, that fluorine is element F. Now, fluorine is in what we'd call the halogens. Remember that columns in a periodic table have the same valence electron configuration, so behave alike. So all halogens behave alike. I should also mention that hydrogen is not a member of any group. It's above the alkali metals, it's above the halogens, but it's not part of any group. And so the alkali metals are the farthest to the left, alkaline earth second to the left, noble gases farthest to the right, and the chalcogens are to the left of the halogens. And again, elements in the column behave alike because they have the same valence electron configuration. And so this question is asking us, which of the following pairs of elements consist of a metal and a nonmetal? And so if you remember the periodic trends, as you go up and to the right, the strength electrostatic attraction between the outermost electron and nucleus increases. And so the nonmetals tend to react by gaining electrons. Now the metals, the red, it's easier for them to lose electrons. They have a lower ionization energy. Now if we look at it, selenium is a nonmetal, bromine's nonmetal, and so the answer is not A. Sulfur is a nonmetal, argon is a nonmetal. Titanium is a metal, vanadium is a metal. Chromium is a metal, manganese is a metal. And then we have scandium, it's a metal, and then phosphorus is a nonmetal. And so the answer would be E. But again, please make sure you can relate that to the periodic trends that we've talked about. As you go to the right, the strength of electrostatic attraction between outermost electrons nucleus increases, ionization energy increases, electron affinity increases, and electron negativity increases. And so for which of the following is true? Ionization energy is the energy required to remove an electron from an atom or ion in the gas phase. That is true. As you go up and to the right of the periodic table, ionization energy gets smaller. That's false. Ionization energy gets bigger because electrostatic attraction between the outer electron and nucleus does get bigger. The stronger the attraction, the more energy required to move the electron, the larger the ionization energy. Which of the following is true? Metal elements tend to react by gaining electrons. That's false. Metals tend to react by losing electrons. Remember, metals are in the lower left of the periodic table. They have smaller ionization energies. Alkaline earth metals, which is this column here, they tend to form +2 ions. And so II is also false. The alkali metals typically form +1, so metals tend to react by losing electrons. The halogens tend to form -1, and the chalcogens tend to form -2 ions. Which of the following correctly lists the atoms or ions in order of increasing ionization energy? Now notice we're given a list of atoms without a charge, and for those we can just use the periodic trends. And so francium, it's in the bottom left, and then you have phosphorus and neon. And so as you go up and to the right, the strength of the ionization energy increases, and so I is true. Now for F minus, F and F plus, they all have 9 protons. And then F minus is going to have 10 electrons. And F plus will have 8 electrons. And so the F minus will have the most shielding, it will have the weakest attraction, and so it's going to have the lowest ionization energy. F plus will have the least amount of shielding, strongest attraction between the outer electron and nucleus, and hence largest ionization energy. Now if we look at calcium 2+, potassium, and then argon. So calcium has 20 protons, potassium is 19, and then argon is 18. So argon has 18 electrons, potassium has, this should be a +1, 18 electrons, and calcium ion has 18 electrons. And so these guys are isoelectronic, meaning they have the same electron configuration. And so the more protons, the stronger the attraction, the higher the ionization energy. And so the calcium +2 should have the strongest ionization energy, and the argon would have the weakest ionization energy. And so the answer is going to be B, only 1 and 2. Now for this one, it's asking which of the following correctly lists the atoms or ions in order of increasing radius, so increasing size. And so remember, as you go up and to the right, ionization energy increases, but size decreases. So we have yttrium, molybdenum, and silicon. And so silicon should be the smallest. And so I is false. Now in terms of II, you remove electrons, it's going to get smaller, so Cl plus should be the smallest. And we're asked to put it in order of increasing radius, so II is false. And then we got neon, F minus, NO2 minus. And so neon has 10 protons, fluorine 9, oxygen 8, and neon has 10 electrons, fluorine minus has 10, and oxygen 10. And so they all have the same number of electrons. Oxygen has the fewest number of protons, and so have the weakest interaction. And so O2 minus, we'd expect it to be the largest, and neon should be the smallest of those. And so the answer is just going to be D. So hopefully you can now describe how the electrostatic interaction between the electron and the nucleus increases as you go up into the right periodic table. You should be able to describe how the size electrostatic interaction between the outermost electron and nucleus is related to the size of the atoms, electron negativity, ionization energy, and electron affinity of the element. You should be able to put a list of elements in order of increasing size, electron negativity, ionization energy, electron affinity. You should be able to describe how an atom gets smaller when an electron is removed and gets bigger when an electron is added. And you should be able to put a list of ions in order of increasing size, electron negativity, ionization energy, and electron affinity. I hope that helps.